Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So thank you for listening to me, and I hope you will enjoy my talk. So what this talk is about is I will try to convince you and sell you two concepts. The first concept is that named data networks, ICN in general, but specifically named data networks are the technology to be used in cars for car-to-car and car-to-infrastructure communication. And the second concept is we'll introduce a technology that allows to basically geo-route the names instead of just blindly forwarding them to somewhere else, to like all the places you have. So basically, those are the two things of this talk, and let's start with the first part. So I spared you, actually don't spare you, but I tell you very briefly the importance of connected cars is becoming more and more important. And actually car manufacturers today have their car connected using 3G. And that will change because basically the amount of data demand is growing fast with autonomous driving and with all sorts of applications that are going into the car. Just to be clear, we are talking about machine-to-machine communication mainly, rather than user involved, okay? And basically, we know that cars can have infinite energy, they can be ideal nodes on a network, and they can basically play a number of roles, like consuming data, producing data, or carrying data. NDN. I'm sure you heard at least the second paper that was saying that ICNs are bad and CDN can actually do them. The same stuff with much less pain. I think what was the second paper. But why we are interested in NDN on cars? Well, the first thing is that moving away from IP, so basically to an endpoint that is tied to a physical device, helps a lot when you have things moving and moving fast. So basically, the host-centric IP has a lot of complexity to be handled in order to handle mobility and multi-homing. And then I'm not saying that you cannot do it, but there are more natural ways of doing it. If you address things by name, so you're addressing the data rather than the car that produces the data, basically you are decoupling the communication from the interface. And the reason why you can do that is because basically the data is usually redundant. So you have many different copies of the same data. The class, yeah.
So I just understand the scenario you have in mind, because you mentioned autonomous driving, right?
Yeah.
So with the measure autonomous driving, I'm interested in cars that are nearby.
Sorry,
if I do autonomous driving,
yeah.
I'm probably interested in communicating with cars
around
me.
Yeah.
So in that case, I'm interested in the specific car,
rather
than just generate the content.
I think you are more interested in the information, right, rather than the car.
Well,
you are interested in
related to a specific car.
To a specific area ahead of you. That's what I would think. But I don't know. I mean, we can discuss this, but what I would think is that your car wants to know if the car ahead sees something that is relevant to drive, right?
And you can say any of the cars.
Yeah, any of the cars ahead, right, or behind, or so. And sorry, naming the data basically what does is decouples the problem. And one of the natural examples, my computer sorry keeps fading, is one of the natural examples is that basically think about you are interested in knowing a parking information or a traffic information. You don't really want to select a car. You just need to know that parking or traffic information from a specific area that you're interested in to go, but car A, car B, car C doesn't really matter at the end of the day. So that's one thing. And the other thing is like if you look in terms of interests and data, that is what NDN does. Basically, you send an interest with the name of the data you want, and doesn't matter who does that data, but that allows also you to send the interest over multiple interface or different interests over multiple interface, so you can easily handle multi-paths, multi-homing, and basically that becomes some sort of a natural thing without playing any sort of trick. So the application in this case names the data, as it wants. And basically, some applications are really trivial, some others are less trivial, but basically, and the network understands the naming and uses that to forward the packets. So I'm sure most of you have read enough on ICM, but just a quick refresh. Basically, the idea is that you move from an IP, and so you connect it to a machine and get something from that specific machine, to the idea that you send an interest that has a name, that interest travels the network, and basically is understood by the routers, that then forward the interest or respond if they have the data. The key components of the SDN architectures are basically few. The ones that are really interesting for us are the content store, that is a cache to every node, and that is actually one of the most interesting parts for the car-to-car environment, because basically means that each car can act as a cache, so can basically act as a data mule and can handle disruption. And then you have the pending interest table, that is basically the one that you use when you send an interest and you're waiting for a data to come back. And basically that lies the breadcrumbs for the paths. And then you have the forwarding information base, that is like a routing table. You basically have a prefix and you match it with an interface. And this is basically the way that the packets are handled. You get the interest, you look if you have something in the forwarding information base or in the content store. If not, you forward the interest everywhere, otherwise you forward to the right interface. And this is basically this architecture of the general NDN router, and it's nothing new from the point of view of the car. What we try to do is basically try to use this architecture in the vehicular network. And now, vehicular networks are quite interesting, because if you think about how they behave, they change topology basically every 10 seconds or less, both V2V or V2I. And so basically your topology is kind of very dynamic. And that means that you need to continuously reroute. And what we perceive and we think is that NDN allows you to kind of cope with such frequency of rerouting. So we designed a while ago a version of NDN for cars that is called V-NDN. And basically what that does is uses the NDN approach on the cars. And each car can be either a producer, a consumer, or a forwarder, or a mule, because we took the hard decision of basically storing every data you see. The car stores everything. Not only that, the other thing is we decided that since we are assuming the cars are connected through a wireless medium, that is easy, and today is Wi-Fi, basically every transmission is done in broadcast. So there is no unicast. When you transmit to everybody, and we developed in V-NDN a mechanism to kind of lower the number of retransmission to control the flooding. But it was still a flooding. Okay, so basically what we did is, okay, each time I need to put an interest on the network, I send it out in broadcast, and then I use the GPS location of the car, the receiver, and the sender, to determine which is the car that is the farthest away. And so basically I can somewhat propagate the interest just with the longest jump possible. And this was done indeed for V-NDN. And basically in this way you could, using the broadcast, disseminate a number of interests and get some content back. Now, what I will introduce now is basically an evolution of this concept of flooding the network. I mean, it was controlled flooding, but was flooding at the end of the day, to something that is a little bit smarter. And the idea is that we could probably put a shim layer between the network layer, so the names layer, and the Wi-Fi layer that can somewhat handle the concept of geographical forwarding, and therefore not flooding the network. The key idea is we could bind names, actually prefixes, to a specific geographic area. And in doing that, basically, after we discover where the content is, from that point on, we can keep forwarding towards that area until we see that that area is no longer a place where the content is. So basically, we developed this link adaptation layer that does the same thing, that does this thing. Basically, instead of blindly flooding, we go to add a couple of intelligent blocks. One is we introduce the concept of geographical phase. The geographical phase is a virtual phase that appears to the router as a regular phase, but actually binds names to a geographical area. And when an interest is issued, the first time you need still to search because you don't know where the content is. But once you search and you get the content from a specific area, basically you can, at the end of the day, bind that content to that area. From that point on, you just do Dijkstra on the roads to that area. And let's now get in the details. So the first step is I need to see where I am. So I take the world and I map it on a mapping, on a georeference system. We picked the military system because it's very convenient to size the area differently. And it's very easy to do that. And basically, you have a map, and you have a grid, and that each tile is 100 by 100 meters. Then we can identify two types of application, right? One type is I want the parking in whatever place here in Cambridge, and that is easy. You could basically bind the name to the interface, because if you want a parking in front of Christ Peace, I don't even know if there is one, but basically you just route directly there. You don't need to do anything else. Only the cars that are in that area know if there is current available parking there. Anybody else doesn't care. Now let's take something that is not location-based. Basically, say you want to listen to Spotify in a model where part of your data comes from the networks, like from the internet, and part of your data might be cached in other cars, because at the end of the day, media is an interesting content because can be cached by popularity, so basically you can exploit that thing. So when a node gets an interest, say, for a non-location based data, what happens is, first of all, if you don't know where it is, you just forward in all possible directions, because of course you need to find what is the source of the data. Then at some point you will find the data, and when the node basically arrives to another node that, well, the interest arrives to another node that has the data, what you will see is that basically you can map that node to the tile, and then basically you can piggyback this information using the layer 2.2. Since basically this is all broadcast, right? Every node on the path will learn the position of this data, and so basically you start building a position where the data is, and you register on the fib that is the same of a routing table where that data is, and from the next packets on, you basically can start sending the data to the geographical interface that handles that specific area. So basically the idea is the first time I register in the fib a new phase, I associate the prefix of that data to that new phase, and then from that time on, I just basically go to that phase. And that's what means at the layer 2.5, you can associate back that phase to that geographic location. So basically you can use it to route really in that area. So how you do? Well, we said no match, flooding. When the content comes back, I register the phase. After that, I have two cases. If I have basically multiple phases that are going to the same direction, that I have the same prefix, so say /Spotify /song1 /chunk2 or whatever, you basically can round robin among the interfaces that have that song. If you have only one, you just use the interface for 95% of the traffic, and you keep exploring for the other 5% because you don't want the phase to dry out. You may have an area in your map that basically that area has, say, 70% of a song, but there's still 30% missing. So you want to keep discovering what is going on in order to not find yourself totally in the dark at some point. And of course, you need to have some timeout so that that phase is no longer producing data for that specific interest you don't use. You remove that phase. Then, in the link adaptation layer, this is the network layer scene, right? The network layer you just send to a phase, and you know that that phase will solve the problem. In the link adaptation layer, what is that each geo phase will basically takes care of the real propagation of the interest and of the data. Basically, what does is takes the data coming from the packets from the network and sets it to the right geophase so that the network layer can send it to the application. And also takes care of registering the fib with the correspondent geophase. Not only that, basically, if you look from the flow point of view, the packets come from the ad hoc network or from the infrastructure, and basically looking, each packet has basically a number of stuff in the fields, like the nonce is a random number to avoid loops, and then we have a metadata that tells you what is the previous hop position and what is the destination area. So once you know these two information, what you do is you basically register it on the routing daemon and basically register the phase or create the phase if the phase doesn't exist. On the way down, when the packet is routed back to the same phase that identifies an area in a static way. And so from that moment, what you do is you calculate the shortest path to that destination area. So if you are saying a specific road, you need to go to another location of the city in another area, not even a road. What you do is you calculate a Dijkstra on the topology of the road. And this actually goes back to an old piece of work we did together. And basically, the idea here is that the roads are a pretty stable topology. The cars, you don't really care which cars are on the road. You just care that they came forward for you or they have the content for you, because you are addressing the content and not the specific node. So you are not really interested to see the specific node. And so basically, if you use the road, you can have a much stable routing path. Not only that, you can start playing tricks, like you could give heavier weight to larger roads and less weight to smaller roads. Those heuristics are good because basically larger roads are usually more busy, especially at rush hour, and so it guarantees you that you get somebody to forward your content. Now, when you forward, basically, what you do, each node starts computing the Dijkstra, and so each node knows what. So knows its own position and knows the phase area, the area identified by the phase. So basically, you need to understand which is the best node to forward that packet, either data or interest. At that point, doesn't really matter. And so that basically you minimize the number of network hops. And also you increase the probability that things go, that the packet gets delivered at the end, right? So the idea here is basically that there are some specific locations that are generally better than others. And just to give you an example, a specific location that is generally better than other is the center of an intersection. Because basically you have an open view from the wireless point of view. You basically are sending signals in all four directions, and you basically are in a better position. So each node, what does is looks at the packet and decides its own position, assesses ability as a forwarder, and computes a timer that is basically based on its own position, and once the timer is over, if nobody else has forwarded the packet, it forwards the packet. And if somebody else has not forwarded the packet, basically just drops the packets in the queue. This is a little bit of complication in the implementation side, because basically you need to make sure that you don't send to the MAC layer more than one packet at a time. Because if you do that, you can't remove any more that from the queue, unless you go really deep in the kernel. But if you stay out of the kernel, you really can't remove it. And then once the packet has been sent, you wait for an implicit ACK. That means that basically I wait to hear that somebody is still forwarding the packet. And so basically that means that the transmission went well. The reason to do that is, of course, because Wi-Fi at 2.11 doesn't have any ACK in the broadcast mode, and that can be probably solved by other technologies that behave better than that. But the current ones that are considered for the car-to-car are basically all based on CSMA, and so that is something that generates some of the issues. Now, which packet you forward? Because we noticed, and we will see later in the result, that depending on your policies, you get different results. And this is because when the traffic starts to build up, both the vehicular traffic and the data traffic, you start getting longer and longer queues in the transmission part of the nodes. And this is because basically you start getting congestion. And so we found that actually giving priority to the data packets over the interest packet helps relieve some of the congestion. And the reason of this is because they are larger packets, so you basically get stuff off the queue in faster. And also you can use them to back pressure the previous hop to say, hey, I'm full. And so this is one thing that actually gets a better delivery rate. The second one is that the cars at the intersection have a much larger coverage, usually than the other cars, so they are the good ones to retransmit your packets, to forward it in all the directions. And of course, you want always to pick the farthest possible car compared to the location of the last hop. So the way you do this in an algorithmic way, we chosen to approach the problem with basically timers, so that basically we could avoid, at least partially, some of the issues of continuously recomputing the distance and stuff. So basically, when the red car wants to transmit a data packet, basically the first one that could retransmit that data packet from the red car, so the red car puts the packet in the air, who is the ideal forwarder? That is the question that I'm trying to answer here. The ideal forwarder is the guy that is the farthest away from that car. So it's the one in junction 1. So basically, we built an algorithm that sets timer specifically according to the distance and the location of the car, and if it is a data or an interest. We see that for a data, for the farthest one, you can wait from 0 to 4 milliseconds, and then as it gets closer, waits more and more and more. So what happens if when the red car transmits the data, if there is somebody in junction 1, after 4 milliseconds, the red car will hear an implicit ACK. If there is nobody in junction 1, then slowly the timers will go ahead until somebody will be somewhere. If nobody answers, then you retransmit again, hoping that you get better luck. And of course, the idea is that initially you give priority to the intersections, and then if the intersections are not there, you have priority to the cars that are in the edge. And again, if you have many things in the queue, we queue data and interest, you first get out the interest, and then you get out the data with the same thing, interest and then, sorry, first the data, then the interest with the intersection first and edge later. So in this way, basically what you achieve is that you can do the forwarding in a fairly efficient way with very little retransmission and very little flooding of the network. And the other thing that, of course, happens is that during the forwarding process, those cars that hear the packet, that data or interest, but they are not in the shortest path to the destination area, basically, they do not re-forward. There is no need for them to re-forward because they just actually need to suppress the flooding of the packets. Otherwise, basically, the network will get congested very, very quickly. So we tried this by simulations. And of course, one of the reasons is that is the only way to show results at scale. And we took an area in Santa Monica, 2 by 2 kilometers. And we picked Los Angeles rather than Paris because we have free maps for United States and paid maps for Europe, so the choice was no-brainer for us. And basically, we generated with Sumo, that is an event-driven microscopic traffic simulator for traffic, meaning the road traffic, not the telecommunication traffic, 2 different scenarios ranging between 812 and 1048 cars. And the traffic, the road traffic is shaped based on the importance on the road. I don't know if all of you have been in Los Angeles, but there are 2 major arteries. One is Santa Monica Boulevard, the other one is Wilshire Boulevard. And those are the 2 main roads in that area that we used as the heavier traffic. And then we put 4 RSU. And the way we picked the RSU is because that area is covered by a Wi-Fi service offered by Time Warner Cable. And basically, they have a map of all the RSUs in the area. And so we picked 4 random of their RSUs. They have 25. And you may ask why we cut from 25 to 4, because we wanted to see how much of the V2V could be helpful, and especially how much of the cache could be helpful. And the traffic application we used, was Spotify. I need to say we didn't implement Spotify on the simulator, meaning have the application communicate with the simulator, but we generate the same type of traffic of Spotify that is 300 kilobits per second per song. And this is like the regular one. It's not the extreme quality that is much higher. So then the question we asked ourselves, what was we used to compare and what we measured. So what we used to compare, we picked GPSR, and we assumed that GPSR that actually routes to the node, not to the content, always knew in real time where the piece is looking for is. So we implemented some sort of oracle that told to GPSR, if you're looking for this piece of content, this is the car that has it. And at 0 cost and in real time. That, of course, is not really how things work in life. So then we selected 2 different types of libraries. We initially started with a small library of 100,000 songs, and then we went to a large library of 1 million songs. For the ZPF distribution that we used, we basically, there is a paper on Spotify. I don't recall on top of my mind the exact numbers, but basically we used the ZPF distribution as on that paper on Spotify. It's a fairly famous one that analyzed the application. So what we looked at was initially the percentage of satisfied interest. That means you send an interest, you get a content, and how many of those are satisfied, and against the number of consumers. Now, of course, the more consumers you have, in any SCN, right? Basically, you start filling your caches, and as things go better, you find that initially you have 40% that they go a little bit up and so on, because the cache plays a role. And they go back down because as you go with a higher number of consumers, you get side effects from the wireless side that basically your network gets very, very congested.
Was it 1 interest per song?
No, it's 1 interest per chunk. And chunk is basically 900 kilobytes. So it's 900 KB. And basically, each song is like 3, 4 interest, 5, depending on the length of the song. And we assumed, we had again in that paper, we found the distribution that the song is in the order of 5 megabytes, the average, for that quality. So we assumed that was the size. Then, basically, what happens is we try to understand, because if you look at the interest satisfaction, right, they are pretty low. But then the question is, can Spotify cope? Now, we looked at the buffering of Spotify, and it turns out that Spotify buffers about 30 seconds. That is a fairly large amount of time, actually. So what we did is, assuming that you have a 30-second buffer, so you basically have this sliding window of 30 seconds, how the user satisfaction is, we defined it as basically the fact that the song does not interrupt. Because I can cope probably with lower quality, I can cope with a lot of things, but if I'm playing my favorite song and in the middle of nothing that is interrupting, then I get really pissed. And probably I will not listen to Spotify for the next week or so. So basically, in that case, basically we immediately looked at the fact that if you account for the buffer, you see that the user satisfaction until the network is saturated is actually pretty good. Because you are like in the 70–80% of the cases you have network. And then the reason of that is because basically you are taking advantage a lot with NDN of the caches that are in the network. Because as the song is popular, basically that helps you in getting data from close by rather than from the access point. And the reason why GPSR fails is because GPSR doesn't have cache at the end of the day. Basically, the reason why, even if we gave to GPSR all the possible information, meaning that they had an accurate position for each segment they wanted at the time was needed, and anyways, when they reach that location, the segment is gone, the car is gone. And so they need to basically proceed with a sort of recovery mode. They had in the implementation they have a one-hop search, and if that also fails, they need to re-ask the Oracle and redo the routing. So basically, for this reason, they couldn't cope, and the user satisfaction is much lower. Now, this chart is a little bit different. What I'm trying to show is how much data, how much requests, how much interest reached actually the producer, where the producer in this case is the hotspot, the access point, right? And basically, in order to satisfy the interest. And as you can see, here you can really see the effect of the cache. The fact that basically, as the number of consumers grows, you have less and less interest that need to get to the internet in order to get the data, because basically you find it on the network. While on GPSR, usually you get, because there is some loss in the system, so you need to get a little bit more than one in order to get your data. So basically you're putting interest in the system that actually do not go. And so basically what we show here are two things. The first one is that there is potential for the named data networking as a protocol for cars, and basically to do car-to-car and car-to-infrastructure in order to basically enable connectivity. The second thing is like it's possible to bind names to geographical location and so reduce the need of flooding. And I want to add that doing real proper routing, like really updating the routing table, is something that with that topology changing so much is not really easy to do. And also you could generate a lot of overhead. Another thing to consider when we are talking about car and named data network compared to the fixed environment is that we have, in the car scenario, you have much less need of very large caches because we are talking of speeds, data rates that are, in the best case, 50 megabits per second compared to data rates that are, in the best case, 100 gigabits per second, or in the good case, 10 gigabits per second. So the amount of data you need to cache is much less. And so it becomes like feasible from the system point of view too. And so this is a piece of work that actually we implemented in part. So I will show, before I conclude the talk, a very small piece where you will see two applications of named data networks over the cars. I need to switch from to here, sorry. No, why? Okay, it's there. So this is basically we implemented the full NDN stack. So all the forwarder, all the cache, etc. And we run an experiment with two different applications. And we ran this before building Navigo, and we ran in UCLA basically because I mainly have my 20 cars instrumented there. So for me, it's easier to fly there rather than instrument other 20 cars. And so what you see is the scrolling thing is an accelerated movie. It's basically the interest in the data that is going up and forth. And basically what we are doing is we are requesting either parking information that you won't see because they're going too fast, but believe me, we can slow it down. But also we are requesting pictures. And the way we request pictures, it's we request picture of an intersection or of a piece of road. So we are routing geographically to that intersection or to that piece of road. And basically the picture is taken when the interest is received. The picture is not pre-taken. Like when you see a picture, is actually something that was taken at that point. Yeah, they are not the most beautiful ones because the laptop was sitting in a very awkward position. But basically, at the end of the day, this has the full stream of things. Basically, the application is running on top of NDN router that is actually running on real car with real Wi-Fi and so on. And in this specific scenario, we had both Wi-Fi and WiMAX, because at UCLA, I have access to our own WiMAX station. So we basically can have our own WiMAX and schedule it as we want. And so as you can see, the system is able to actually behave properly, to route the interest, to get back the data. And what we discovered at that time was like that caches on this run were basically satisfying about 30 to 35% of the requests. So we did also one thing that was very awkward, that was basically issuing an interest for a picture and then remove the guy and then issue an interest for the same exact picture. So basically what you get is that the producer cannot produce a new one, but if the picture is still in the caches, the second request, the third request can get until the caches are evicted, basically the thing. And thank you. I hope I didn't bore you too much with these funky card things, and I look forward for questions and being beaten up and so on.
Are there any questions?
Okay, maybe a quick one about the traffic pattern and the caching, and maybe I missed it. So when you talk about Spotify and songs, how often the songs are actually the same? Or
So basically, the songs, we use a zip distribution. Taking on top of my mind, but off the record, we go to the paper because I don't really remember it. Spotify declares that basically about 70% of the song, 20% of the song makes 70% of the traffic. And there is a paper, I don't remember if it was a WOMOM or something like that, basically does a thorough analysis, and we talk their zip distribution, somewhat making an act of faith.
Yeah, it's fine.
Yeah. Paolo?
Yeah, I'm not nice, but do you have a sense what would be the performance if you just use 4G? Because 300 kilobit doesn't really strike me as a super high bandwidth throughput, right, per car. Like, I can use Spotify, happily in central London with no problem.
No.
Now, I understand when you are like, many of people using that, then of course you're hitting. I'm just trying to understand at which point, effectively your technology becomes.
Well, that's okay. Let me answer. I agree. 4G until you get to clog the network is okay. So in the 405 in Los Angeles at peak hour, 4G doesn't really work too well. But the reason was not this. The reason was that in this way, most of the traffic doesn't go on your paid gigabytes, right? Most of the traffic gets off that. And now, this is we can argue that it's not important or is important. As a matter of fact, depending who is paying. Meaning that, especially if it's delivered by the car manufacturer as a car application, that becomes extremely important. Because they are paying like 3 cents per megabyte or something like that, 5 cents per megabyte. So
it's a business argument or it's a technological argument?
It's both, in reality, basically. From the technology point of view, I cannot argue that 4G gets fully, depends on the planning the operator did, right? And then you can counter-argue me that if you have a request, the operator can add tower. So, and on this we can argue forever, because we could go to nano cells, and then capacity can go very high at the cost of installing a cell every 100 meters, right? And on the other end, in today's deployments, or at least in the US, in today's deployment in US, the 4G gets pretty busy. I don't know the UK status. I don't talk about the France one because I have an horrible provider, so I can't say anything good about it. And but in the US, we tried on the freeway when it's really rush hour, and basically your throughput is close to zero. And from the business point of view, there is the issue that you may not want to consume your cap. Spotify is an heavy weight thing. But yeah, I agree that you. No, I'm just curious. Yeah.
Because, I have no idea because I like a lot of this. I was working with projects. The usual pushback was that 3G, 4G. We're always. I was just trying to get a sense for where today is the position.
I can just tell you not much more than, but one thing I can tell you, there is a couple of companies that are really working towards the idea of getting most of the traffic offloaded from 3G, 4G. The main reason for them is costs. And there's really costs.
Okay, any more questions? If not, let's thank you very much.
Thank you.